Hello, viewers. Thanks for joining us today. We have one of our mentors on the Embedded Learning Challenge. His name is Tochukwu Nwoke, and he's going to be talking about tiny machine learning. He's taken the course, he's read the book, and he's a mentor. So he's in a good position to talk about what it is that you'll be going through. So, bringing Tochukwu up.
Hello.
Hi, Tochukwu.
Hi. Good
Welcome.
morning. Okay.
Morning. Okay. So the floor is all yours. Um,
Yeah.
yeah.
Just 1 second. Let me. Okay. Hello, everyone. I'm Moke Tochukwu, a machine learning engineer. Also interested in embedded systems engineering and TinyML. So I'll be giving an intro to machine learning, to TinyML. Let me share the slides. 1 second. I want to share my slides. Okay. So this can you see my slides yet? Sorry, it's taking a bit to go. Okay. So fundamentals to TinyML. So let's by definition, what is TinyML? Um, so TinyML is basically the process of having the ability to run and execute machine learning workloads on embedded devices, also known as microcontrollers, on extremely low power and at extremely low power and cost in order to enable optimal intelligence. So the idea of tiny machine learning is to run my machine learning models or machine learning intelligence on little devices and save power and cost at the same time, and also give optimal intelligent experience, right? And the reason for this is basically to try and reduce the computational costs and also reduce the latency between latency between where the data exists and the processing interface between the data source and where the data is to be processed. And in order for TinyML to be enabled, there has to be a clear and optimal interaction between the three major domains it encompasses at its core. So when I say major domains it encompasses at its core, I'm talking about how do we um, how do we build or design or orchestrate a tiny machine learning solution or process. And at its core, it encompasses three major domains. And these domains are the machine learning part of it, the applications part of it, and also the embedded systems part of it. So there has to be a clear definition and interaction between these three processes, right? So at the applications part, we talk about the solution that we're trying to prefer and how we are trying to apply it to a particular problem. So let's take, for instance, there is a there is a there's a research program and also a solution around trying to save elephants, and they have been embedded or little devices mounted on these elephants' collars to be able to track and monitor their movement, right? So the idea is to try and be able to understand why and how to apply a certain tiny ML solution in a problem or to a problem. And that is how the interaction between these three core elements or core domains within ML comes to play. You have to also have the machine learning part that also tries to give you a smart and intelligent um, path to okay path to the solution. And also the embedded system part is basically what carries or where this solution lives on, because it is small and it's easy to move and it's cost effective and it's also power optimal, right? So these are the three main or the core domains or for interaction within the TinyML concept. Yeah, I can see that. Okay. So let's move on to the next. The components of TinyML. So the components are basically the moving parts. What what um, what are the things that make up TinyML? So the moving parts within the TinyML concept are basically the core components of TinyML encompasses machine learning and embedded systems. So those are the actual moving parts of the TinyML system or of a TinyML system, TinyML solution. So we'll discuss more about these individual components and how they come to play in the whole TinyML solution. So let's take for first of all the embedded systems and the machine. So let's take the embedded systems. So embedded systems are small and constrained devices that are used for specific purposes. So if you come from a IoT background or an embedded systems background, you most likely have encountered or played around with embedded devices. And you know that they are really small and tiny devices that can fit in almost anything. And they are really cool devices coming up that can be stick to your skin, very flexible, very versatile, and easy to use, right? And they are constrained in the sense of the ability or the the applications of their use cases. So when I say constraint, in if you have a when you use your general purpose computers, by general purpose computer I mean your systems, your mobile phones, your smartphones, and any other complex computing system that you've encountered or interacted with, you'll be able to have the ability to do a lot of things, right? A wide range of things. And in embedded systems, but for embedded systems, you have the ability to do one particular thing or a particular task. So they don't have a lot of memory, they don't have a lot of computational power, they don't have a lot of resources in terms of being able to interact within a wide variety of tasks to perform. So what do I mean by that? So an embedded device, an embedded device might be skewed towards doing one particular thing, and that particular thing might just be to monitor or take note of the the readings of a part of your heartbeat, and that is what it performs, and that is and the chip or whatever has been programmed to that device would only be able to perform that particular task because it has been programmed from its manufacturers to perform that particular task, or has been pre-programmed or post-programmed by an engineer to perform that particular task. So they don't really have a lot of power or storage or memory to perform other tasks like play music and at the same time browse for you, because um have the ability to go on the internet for you, because so they don't have the normal input and output peripherals that our computers or mobile devices have. So and and this is a hardware component on which we run our programs and applications like machine learning programs. They compose of microcontrollers for their computational operations and sensors and actuators for their I/O operations. So when I said they do not make use of the normal input and output peripherals that or components that we use to perform tasks on general purpose computers or mobile devices. This is what I was talking about. The sensors and actuators are used to perform operations or give in input signals and receive output performance from these devices. So you won't find them using keyboards. You won't find them, but you can find them using speakers. But these speakers are also sensors. You have speakers on your system, right? But the way they also interact with these speakers are different. You have to manually configure them because they have to be because they are constrained, like I said. So the interaction, the input and output process of embedded devices are totally different from that of the general purpose computers. So let's move forward. We'll talk more on embedded devices as we go on. Let's also talk about machine learning devices. But first, this is what an embedded device looks like. You can also see one here. I have one. So you can see how tiny these things are. You don't expect them to have a lot of compute power. Uh, if you've ever opened your general purpose computer, which is your PC, you will discover that they have really larger boards, but you can see that they just have really tiny boards and really tiny chips on them. So they have limited resources, even in size. So let's get back to the slides. Thank you. Machine learning. So what is machine learning? Machine learning is a subfield of artificial intelligence that focuses on developing algorithms that learn to solve problems by analyzing data for patterns. So if you come from a software engineering background or an engineering background, technically, you you will know that when developing solutions, you have to code in the logic with if else statements or whatever logic you try to design for your system, right? Or you try to capture for the solution that you are building. But in machine learning, we try to use the data itself, that is, whatever information we're going to be interacting with in the real world and have that solution give us the logic that we need. So it is going to be able to monitor or understand the data pattern or structure within a particular information and give us the output that we require based on that. So thereby modeling a solution from the data, not from our own ideologies or concepts or beliefs. So that way, it gives us a more optimal solution to whatever we're trying to solve. And it uses big data. By big data, we mean plenty of data and mathematical algorithms to make observations about interesting patterns in data, which also requires huge computational power to run them quickly and efficiently. So the word big already says it all. It's a large amount of data, right? Passing these big chunks of data through a complex mathematical algorithm, which is basically a number, usual ones and zeros and stuff, and just numbers basically. But having that large amount of data understand being understood by these complex mathematical algorithms takes a lot of computational power and processes um, when running them, right? So if you're familiar with machine learning, and you've tried to, let's say, run a machine learning model on your PC, or even just familiar with machine learning, right? You understand that, or you know that whenever you run these models, you begin to see your system heating up and really spinning fast because the processor is trying to um, fix and try to understand and run the mathematical calculations the behind the scenes for you, right? And be able to model your data or give you an output. Either ways, running these processes require large amounts of computational power, and in turn, that also requires large amount of power from the system. So when your processor keeps running things, right, and tries to run a lot of things at the same time, you will figure out that your battery runs down quickly. It runs down faster than when it's not running anything. So you can try this experiment after this. Let's say if you're Chrome tabs, I believe everyone has Chrome tabs. If you open 20 Chrome tabs, right, and you leave them on for, let's say, an hour, right, monitor the battery performance after 1 hour and see what percentage you have. Then turn on your system again and do not run anything, and you will see the difference between when the processor is running something and when it is not. So that is how that's how power hungry this logic and this approach to profiling a solution can be. So now let's next slide. Why TinyML? So the question arises: why would we want to run this complex algorithms on these tiny little constrained devices that are limited, right? Why? So, so why is it important, and why do we need to do this? As we continue to evolve into a technological advance race on species, the need to have intelligence that can assist and optimize our day-to-day activities becomes more in demand. So let's take for instance, let's just go back to the old days, like when we were younger, and we recited. Like for me, I recited things like we have machines to help us do stuff. Why do we have machines? And the answer was always in my primary school was always we have machines to help us do stuff better, try to optimize our work processes, and also help us optimize our time, right? And that was the idea around having tools to do stuff for you, because if you're going to the farm and using your hand to if you try to use your hand to farm your crops, it will take more time than using a hoe and other farm tools, right? So that's the idea, to optimize our life, to make our life easier, to make our life better, to give us more time to do other things and optimize our performance, right? That is why we need machines. And when we then have machines that are intelligent and can make decisions based on the data without us manually having to, give input or give a lot of feedback to that machine, it works better for us because, to be fair, the concept of AI is being admired by everyone, right? Um, we want to have intelligence everywhere and at all times. So as we grow in as a tech as a technological advanced race, we want to be able to have more time to do other things, right? And we want to work smarter. And if you look at 10 years ago, when we had when there was less let's say there was less amount of interaction between the internet, like internet is easily accessible everywhere right now. You can access internet everywhere, and the amount of information you get can actually be constrained to you, and you might not be able to have time to do other things or even access other information because you have just limited amount of time to just concentrate on one thing, right? But we want to optimize that intelligence and take out the important bits we need and move on to the next thing, right? We don't want to waste time on doing one stuff. And that is why TinyML comes in, because we want to be able to do this in an optimal way and have it everywhere at every time. So take for instance now your smartwatches, right? If you didn't have smartwatches, right, you have to have this big stuff this big box that you use to monitor your heart. Let's say you want to constantly monitor your heart rate, right? Would you rather have to go back home or always carry that big box wherever you're going and try to monitor your heart rate? That's why we have those smartwatches to help us monitor our heart rate on the fly, on the go. So we want to have this intelligence everywhere and at all times. That's why I said using our laptop isn't the best solution for an optimal intelligent experience. So you can't carry your laptop to always do things that you feel can be done in a smarter and is an easier way, right? So we want to have small little devices we can carry around and help us do the same thing, right? And that is where Terminal comes in. So what do I mean? So, for example, now let me just give an example to shed more light on this. You need to get an instant notification when someone in a building is in danger based on the current state of events. Um, so the idea is, let's say, in a mall or in a workplace, in an office, you tend to have someone get into like let's say is in danger, how can you tell that the person is in danger, right? You want to have a camera placed somewhere, right? And you want to have that camera um, be connected to a system, let's say in the cloud, right? On a computer connected to the cloud, because you want to be able to perform, you want to be able to detect a particular situation. And you can't do that by coding software, right? You need a smart way to do that. And this is where machine learning comes in, because um, machine learning can enable us understand stuff just by looking at pictures, right? So we want to be able to quickly detect when there is danger or someone is in danger and act on that. So think about having, let's say this is one way. Think about having um, that camera responding to you after, let's say, 1 hour of the event happening. It doesn't make sense, right? Also, think about having these big cameras that consume power, because the bigger the camera, the more power it consumes. When it's also connected to the internet, that's more bandwidth. It's streaming that data. That's more bandwidth. That's more latency to the cloud, and performing that process of understanding what type of event is occurring at that point and sending that data back. So the time between sending that data to the cloud, running the process there, because these algorithms are expensive in computational costs, as we've already established, and we're sending that data back. The perpetrator of that particular event might have already escaped, and there's no point of the solution already. So these are some of the things that um, TinyML can help us, or why we need TinyML in our society. So, like I said, I already stated all that is on the slide. So, plus, like, it can be quite messy to connect wires every time and have them connected somewhere from these big cameras and stuff. But we'll get to understand how TinyML helps us to do that better in a bit. So, so the question becomes, we need another way to do this, which has uninterrupted power complications. That means if that camera runs down, let's say you have power outages and that camera cannot be powered, well, there's no point of the camera being there anyways. Then you can also have, sorry, then you want the camera, or let's use the camera, because you want the camera to live close to the data, which is where that action or event is happening, and be able to process it near real time. That is almost um, at the instance, that is, let's say, a maximum of 1 second from when it happens, and give you that information, right? And also, you want a cheap way to implement this, and this is where the concept of TinyML comes in. So, but before that, let's remember that these devices are really constrained and they are limited in what they can do for us, right? And we have these also big algorithms that are trying to fit on this thing. So let's look at the challenges that come up when trying to or with TinyML. So, for starters, the challenges in TinyML will be viewed from both parts, right? From both sides of its core component, which is the machine learning side of it and the embedded side of it. So, let's look at the embedded part of the situation or challenges that we might face when trying to implement um, TinyML in details. So the area is divided into two. So so we have the hardware challenges from the embedded perspective, and we also have the software challenges from the embedded perspective. So let's move on to the hardware challenges. So on the hardware side of things, which I consider the most important, because to be fair, we need somewhere to run these programs. We need somewhere where we can have this intelligence live, because they can't live on the air. Obviously, they have to live somewhere. So we need something that can sustain them, or where they can exist. But the issue is that we want to run these resource hungry programs, which are ML programs, on resource constrained devices, which make use of microcontrollers, because basically they are basically microcontrollers rather than general purpose computing devices, which make use of microprocessors. So, in order to understand what embedded devices are in detail, understanding what they are made of or what they are built on is very important. So microprocessors are, I'll just give a brief detail about this so it just gives more understanding. Microcontrollers come with a microprocessor, a RAM, storage, every other thing really constrained in one chip, and everything has been cut down to fit on the purpose of or the specific purpose of that embedded device. So that is what microcontrollers are. And that is the design or the order of how they come in. But a microprocessor is basically a chip, and in general purpose computer, we have this microprocessors standalone and then connected to other things like the storage, the power output, the input output um, processes. But they all live kind of independently on the process or the board logic, right? But in embedded devices or microcontrollers, they are all fitted into one chip to manage the resources and the purpose of which they are run or executed, or what they hope to accomplish. So that is the fundamental differences, right? But the microcontroller does have a microprocessor just constrained on it. So in order to appreciate how this the challenges or how these microcontrollers can provide the same solutions for us as devices which have microprocessors to run their processes individually without being attached and constrained by other things trying to fit into that chip. We need to understand the differences and see how they actually perform that solution for us in a very optimal way. So this is the order of magnitude of difference between devices that run on processors and microprocessors and basically a microcontroller, right? So you can see the platform is basically a PC, a laptop, and this is a microcontroller. You can see the compute requirements for a microprocessor is usually around 1 gigahertz to 4, and that is a large amount compared to that of a microcontroller, which has one megabyte more 1 megahertz to like 400 megahertz. That is already a 10x difference between them, as you can see. You can see this is 10x greater because if you like from the gigabytes to mega values of the SI unit, you can see the difference is already large enough, right? And on the memory part, this microprocessors have microprocessor power devices can have memory of 500 MB to 64 gigabytes, right? And you can see that of the microprocessor is really, really small. It's running on kilobytes, 2 kilobytes to 512 kilobytes. That is 10 10,000 times smaller. That is really small. And same thing for the storage. You can see they have 64 gigabytes to 4 terabytes, and we're having this is way this is 100 times um, bigger than that of a microcontroller, which runs on 32 kilobytes to 2 MB. Same thing for the power consumption, right? So when we charge our devices, when we charge our devices when we power our devices, they run on at least 30 watts to 100 watts. And while these microcontrollers run on 150 microwatts to 232 23.5 milliwatts. And you can see the difference in the watts. It's really huge, running from a full 100 watts to micro milliwatts of 150, and that is really, really, really small. And this can be equivalent to the console battery that you have on the console battery you have in little remotes and little devices, right? And that is what these devices run, and they can run on these little batteries for months, for a really, really, really long time, rather than our computers that can last at most, I think, 12 hours or 9 hours for a MacBook or something, and you need to charge them up again. And that is when they're not even running things that are quite heavy. When they're running things that are quite heavy, they can last they can last for a smaller amount of time. So that is quite the dilemma between this, right? How do we fit this? How can we run such powerful algorithms on these little devices? So let's look at the software constraint of the embedded perspective. So on the software constraint of the perspective, there are different levels considering that these devices are purpose built and they're going to be running these programs, right? And the levels on the software part is the operating systems part. Then there is the libraries, which are the default libraries supported or that can be interportable between these devices and that of, and there's also the applications part, right? So on the operating systems, you can see that we have common operating systems, the Windows, the Mac OS, and the Linux OS, and we have the on the mobile devices we have an Android OS and an Apple iOS OS. So, but on the embedded systems, we don't really have an operating system per se because these devices come without one. You have to most times, let's say, flash or put an operating system on them yourself, or maybe a manufacturer that is trying to do something, because you want to have full control of what this device does for you, and you want to have limited and as much as little as you need um, on these devices. So you have to pick, and it's just like going to the market. You have to select exactly what you need, nothing more, nothing less. You can have stuff on your Windows that can be there for months and you will never use them. You can have, I believe you even install apps on your phones that you will never use for a while, and they're just sitting there. I do that a lot. Like I have a lot of um, apps I have on my phone that I put there, and I've never used them. And they're just sitting there, right? And they take up space, right? But we don't want that with embedded devices. We want only resource limited stuff that we're going to be using. And these are some of the operating systems that exist in the embedded system space. But you have to pick what you want from them and have them flashed on this. That is even if you need one, because sometimes you don't even really need an OS on these things, right? You just need to um, put on bare code on them and have them run whatever you want. There is also the Yocto project, just to mention a few, so you can research on that. But these are the kind of challenges we faced in system. So the problem becomes, how do you even work on stuff that doesn't even have an operating system? This is just bare, just like writing ground ground kernel code on this or ground bare layer codes on this, right? So on the part of the libraries, if you have code, let's say a Python script, right? You have a Python script, and you have a system that comes in 64 bits, you have system that comes in different bits, but at the core of these systems, right, at the core of these systems, that is on the low level of things, they run on bits for the integers or the values or the binaries. Basically they have values at the back, right? For like number 7 has a binary value in bits, right? And these bits are assigned single precision values that have at standard for all devices, right? And they have the bits bar that I talked about earlier, which can which are used to run operations on the lower level of things for these systems. And if you have a code that runs on a Python code, just a Python script, not a Windows special program, Python script. You can run that same Python script on a Linux system and it will work, right? Because the values that which it runs processes with on the computer, the floating point units or the floating point standards are the same. Like they can run a wide range of floating point values. So they're not limited to 1 bit values or 8 bit values or 32-bit values or 23-bit values. They can run values on different single precision unit or floating point units, call them FPUs. Right. So how do we but on the on the you can see here that you have this is for the pi value. You have 3.14, right? And this is the other binary value at the back on the lower level of things. And this can be run on different devices, right? And over time, there have been more logic that have been put in place like this to make them run faster depending on whatever system. So this enables full portability across devices, from Windows. You can run program on Windows, and you can run it on Linux and Mac, right? This is the logic behind the processors, the FPU processors that run FPU logic that run these arithmetics on the lower level for your systems, right? Then on the resource constrained devices, it's quite different because you can't have this logic, this complex logic running the same thing for you on this device, right? You need to have something limited. Like if you have if you're familiar with ARM processors, right? The Cortex M4 and M0 and M7s, you understand that the what they can run is quite different. Some of them run on um, single sign bit integers, while some can run the floating point values, which have the 0.00, but some can just run single digits, right, to make their processors run faster, basically. And that is what happens with this, right? It then brings a problem of portability, right? So you can see that on the universal on universal code, which is basically running stuff on your general purpose computers, you can run them across all. They are portable across everything, but they come at a cost. They come at computational power because these processors have to run these large values for a long time or more efficiently, and also there's also more engineering effort in designing the logic behind it. But that of these devices, which are low code portable, because the logic that can run here might not be the same logic that can run on another microcontroller or embedded device. So, sorry, they have to sacrifice portability across system for efficiency in the system performance and power efficiency, right? So that is the difference between running code or running these programs or different programs across embedded devices. It is not portable across devices. So how do we also manage this? These are some of the challenges on the software end of things. So now let's go to the machine learning part of the problem. So, like we stated earlier, the machine learning algorithms are growing fast in complexities, and therefore the computational capability that is needed to run them is growing and comes fast as well. Near to learn is growing and comes fast as well. And because of this, there is more need to build larger and more powerful dedicated processors that can run them like the processors we have on our cloud servers, right? So if you're going to train a model, most times you have to train you running them on your system will is very detrimental to your system because of the um you don't want to kill the processor on your system. You don't want to harm the processor. You want to take care of that and use the ones on the cloud, right? And those ones have been specially built to be able to accommodate the complex values that are going to be run within this algorithm. Remember, I said earlier that these machine learning algorithms are basically complex mathematical algorithms that have to do with a lot of numbers. Then these same numbers are going to still be run through those complex logic within our low-level FPUs, and this is a very complex mathematical computation that has to be done on the low level of things, right? And special types of processors have been designed to able to manage and accommodate those kind of heavy lifting or heavy computation, like the Google Cloud TPUs we have and NVIDIA GPUs on using GPUs to run these models, right? So how can we run something that runs on a GPU on this? That is where the question comes in. And with that, you can see also the trend in the way these devices has been growing. You can look at some of the, if you're familiar with the popular GPT-3 model, which is recently, which has been gaining a lot of traction lately, and Dali and whatnot, you can see that on this part by 2016 we had larger, we call them large scale, during the large scale era of larger models coming up, model architectures, more complex mathematical algorithms coming up, right? You can see the trend going up, and you can see where GPT-3 is, and you can look at the the training compute for these devices and for these algorithms are quite large in large decimal values, right? So these are how expensive and how large these mathematical algorithms are. So then there's a lot of data that there's also the data part, like I said, right? So the data part, basically a lot of data that is being used for machine learning is collected using these little devices in form of telemetry, but just about 1% of data is being used when performing machine learning. So if you're familiar with IoT, or you're familiar working with embedded devices, you understand that you can monitor stuff that happens every second. You can monitor stuff by minutes. You can monitor stuff by hour, and you can pass that data or send that data somewhere, right? But but the amount of data that is being used, because these things are always on because of they run on really small cell batteries, right? They're really on, they're always on, and we want them to be able to do stuff for us every time. We want them always on and always active, right? We want them very active at all times, right? So how do we do that, right? The problem becomes the data that we can get from them. We use less than 100%, which basically about 1%, because we don't want to always be sending data every single second to the cloud or to another endpoint because of the bandwidth cost. Because this is very costly to be sending data every single time. There's also the power cost again, because this will cause the devices to always run down because they are connected over Wi-Fi or Bluetooth or over a wireless network, and also sending data at the same time. That is more computational cost, and that is more data that is being sent, latency between transferring data. And sometimes we might not even use all that data, right? So how can we make use of all this data that is available to us at right from when they are produced, without skipping some, taking intervals to use them, or picking just selected parts of data that we need. I want to be able to make full use of this rich data that is being given to us at the edge, on the edge, that is at the place where the data is being produced, like I said. Well, this is because they aren't processed at the point of collection. Rather they are to be transmitted to the cloud where they can be processed, and this is costly in terms of bandwidth costs of transmitting this data. That is why the humongous amount of data cannot be transmitted for processing. Like I said, this large amount of data cannot be transmitted for for processing or to be stored somewhere to be processed later because of the cost of the bandwidth uh, sending this data every time. So we want to be able to um, process them with TinyML at the point of production and make use of them to give better insights. So in that way, we are able to actually make use of them and not waste that data when it's being produced, rather than skipping them. We will actively process them on the edge or on these microcontrollers while they are being produced, rather than just waiting for intervals and picking selected amount of data and not making use of everything, right? That is what TinyML can do for us. Now, how can we do that? Since these ML algorithms are quite complex and expensive to run and to use, right? ML models, the ML algorithms, right, um, has evolved over time, and they keep getting larger, like I said. But we can we have techniques in place to compress and reduce the amount of computational values, or those numbers that run stuff the within our machine learning models or machine learning algorithms. You can reduce the number of calculations that happens um, within the mathematical algorithms of the machine learning algorithm. So that is what we'll try. This is one of the approaches we use to try and reduce the size of these models to be able to run on our little embedded devices. And there are different types of methods or techniques to do this. And one is called pruning. Pruning is basically a technique where we have to take out some nodes, basically take out what I say, a whole value from the function, and kind of take out bits and see, and in such a way that we still arrive at the same answer. But these kind of techniques also, quantization is basically trying to, instead of processing with FPU values, that's floating point numbers, we can run these arithmetic algorithms with basically digits, integers, rather than having those um, values after the decimal included in the logic, which will cost more computational cost, like I stated earlier. We want to reduce them to have only single values, right? And these algorithms have trade-offs, because you have to trade off the size of these algorithms for the accuracy. So whenever you try to reduce these model architectures, or the algorithms, in terms of the processes that needs to be run within them, or the logic or the mathematical computation needs to be run within them, to reduce the size to fit on these devices, you at the same time sometimes reducing the accuracy in most cases, because in some cases the difference isn't really much, but the trade-off is there. But that is the trade-off you also need to be aware of when trying to fit these models on these devices. Then also there's also the runtime, the ML runtime. So ML runtime is basically traced back to the way we design, or the frameworks we use to design these models or construct these algorithms, right? This basically, in the nutshell, they are the frameworks we use to write the code or the program that is used to get patterns from data, basically the machine learning algorithms. But the frameworks, right? So different frameworks, different time. So if you like, you're aware that C and Python have different runtimes, right? They run at different speeds, right? They run at the trade-off between them is different, right? So the same thing for frameworks, right? So the more some of the common frameworks we have are PyTorch, TensorFlow, have ONXNet, we have um, the one with Apple, that should be ML Core or something, yeah. But when it comes to running machine learning models on tiny devices, we can't fit those large frameworks on these devices, because there are a lot of things we don't even need there. There are a lot of libraries we don't even need from those um, frameworks. We just need the limited amount of um, code or libraries from the frameworks, and that is where the runtime issue comes in. So we need to find a way to, or we need frameworks that can fit on these devices, right? And there's something called the the TensorFlow Lite, TensorFlow Micro. That the micro embedded library is the one that can run on this kind of device. There are also other um, TinyML frameworks that like GOT. Um, yes, GOT, and there's one from Python. I can't remember the name currently, but these are kind of the frameworks that can run on these tiny little devices. So the idea and the goal is to be able to find another approach or another angle to try and fit this solution to our devices, and have this intelligent and smart way of working, optimizing our time, our efficiency at all times, everywhere and at all times. And that is why TinyML comes in. That is why TinyML is important. And that those are some of the approaches we take in trying to fit these these devices, or sorry, fit these models on these devices, and making that solution work for us without it's a bit of a trade-off everywhere, but the solution is always optimal because you can't have it all. You can have the 98% accuracy and also have a small model. Like we might get there someday, but the idea is to have that good enough of a solution to assist in our everyday in our day-to-day activities and have that work for us. And with that, I have come to the end of the this virtual meetup, and I would like to say the future is tiny and bright because I am also a TinyML advocate and embedded systems advocate. I love all things small and tiny. Thank you very much. I think we can take questions now. So
Thanks for this session, Tochukwu. So let's wait a few minutes and see if we have any questions. We've got 8 minutes actually
yeah,
before the end of the session. So thanks for this. I hope uh, people find it informative. I see. Okay, no questions yet. Okay, but while we wait, so I know you displayed a board during the session when you were speaking. Would you like to tell the viewers a little bit more about that board?
yeah, okay. This is a Spark Fun Edge board, and it was basically developed powered by TensorFlow also, and basically it has the ability to um, run machine learning processes on it, and it has a Cortex M4 processor on it. It's an ARM processor, yeah, and basically it has another board that is used to pass in information and communicate with the report. I don't have that here. It should be somewhere in my toolbox. But basically, you can connect a camera to this part and have a camera attached to it. It has an inbuilt microphone, and you can also you can also do machine learning on this. So basically, it's a machine learning TinyML, a typical TinyML board.
Okay, thanks for that. Okay, so it doesn't look like we have any questions, so let's just wrap it up. Thank you, everyone, for joining us for this session, and enjoy the rest of your day.